Okay, so we're looking at, we got three forces and they're acting on an object at the same time. And we're wondering what the resultant or net force of the object is, or the net force of all of them are. So if I were to draw these three on an axis, and the dot is whatever that object is, the first force is 15 newtons at 65 degrees. So all angles, the way that they're doing it is all angles are measured from the positive x-axis. So I go up 65 degrees, and there's a force acting of 15 newtons. The second force, if I were to draw it, it's 135 degrees, so it's 90, and it's an additional 45 degrees, and it's 16 newtons. And so that's the 135 degrees is a distance from 0 all the way across. The way that I like to do it, though, is I always measure from the x-axis, which is right here, and that is going to be 45 degrees. And then the last force is 11 newtons at 195 degrees, so that's 180. And then I got 11 newtons here, and that's going to be 15 degrees. Because it was 195, and straight across is 180. So these are, as if we imagine like the dot as being like a teddy bear or something, it's all the forces are pulling in those directions, but the teddy bear can only go one direction. So that's what the net force is, or the resultant force. And to do that, it's actually kind of, it's not too complex, but it can be kind of lengthy to figure everything out. So what we have to do is we have to look at all of these forces, and we have to break them down into x components and into y components, because they're all acting at angles. They're not acting straight in the right or straight up or straight in the left or straight down. So we have to get their components. And the way that we do that is we have to analyze each vector individually. So if I go back to the first vector, and I'll draw it again here, it's 15 newtons at 65 degrees. So I'll draw my 15 newtons, and this is 65 degrees. But that means that if I were to complete this triangle, there's an x component of the force, and there's a y component of the force. Some of it is acting to the right, and some of it is acting up. And this makes a nice little right angle here. So I have to get each of those components, and then I have to add them all together. So looking at the x component, that's adjacent to the angle, so I'm going to use cosine. So the cosine of the angle is adjacent, which is f of x, over the hypotenuse, which is f. So the shortcut is that f of x equals f cosine theta. And then similarly on the y, f of y is going to be f sine theta. So for this first one, it's 15 newtons times the cosine of 65 degrees to get the x component, and 15 newtons times the sine of 65 degrees to get the y component. So I'll go and add those over to my list here. So I have 15 newtons cosine of 65 degrees, and then in the y direction it's 15 newtons times the sine of 65 degrees. And if I go ahead and plug those into my calculator, I get about 6.34 newtons, and I get about 13.59 newtons. So I got 6.34 and 13.59, and that's for the first one. Now the second one, if I were to draw just the second one by itself, the second one is 16 newtons at 135 degrees. So here's my 16 newtons, and there's my 45 degrees that I talked about earlier. And again, I have an x component, f of x, and a y component, f of y, and this is my right angle. So I'll do 16 newtons for the x component, 16 newtons cosine of 45 degrees. But you can see here that it's acting in the negative x direction. This is the positive x direction, this is the negative x direction. So instead, if I calculate it, it's 10.31 newtons, but because it's acting to the left, this is actually a negative 10.31 newtons. And then f of y is 16 newtons times the cosine of, times the sine of 45 degrees, and that's going to be, again, a positive 11.31 newtons. Now the last one, the last vector, is down and to the left at 15 degrees, and that's 11 newtons. So now I'm going to have a negative x component, and because it's going down, it's a negative y component. And here's my right angle. So I'm going to do the same thing. The x component is going to be 11 newtons times the cosine of 15 degrees, which is 10.63 newtons. But it is 10.63 newtons. Oh, I copied. This is 11.31. I did 10. Okay, sorry, 11.31. 10.63 degrees newtons, but that again is in the negative direction. And then for the y direction, it is also going down, so it's negative, and this is going to be negative 2.85 newtons. So then I can go through and I can add up all my x components, and if I do that, I get negative 15.6 newtons, and I can add up all my y components, and I get 22.05 newtons. So this is my net in the x direction, and this is my net in the y direction, the 22.05. So now I can draw another triangle with those two components. So I'll dot that up. So it's F net in the x direction is negative 15.6 newtons. Now this is the head to tail method. It means I take the tail of the second vector and put it on the tip of the first one. So that 22.05, but that is positive, so that is going up 22.05 newtons. So even though we have all these three forces acting, we can sum it up with these two, and then the resultant is what goes across the hypotenuse. So that's my resultant vector. And that's my right angle, and this is some angle right here. So I need to solve for this magnitude of r, and I do that by the Pythagorean theorem. So r is the square root of the x component squared plus the y component squared. And so that's the square root of 15.6 newtons squared. That's negative, but it doesn't matter, it's squared anyway. And 22 plus 22.05 newtons, that is also squared. And if I plug that in, I get 27 newtons. So the magnitude of this resultant vector is 27 newtons. And then I have to get the angle, because every vector has magnitude and direction. So I have the opposite and the adjacent. So I'm going to use tan. So tan of theta equals, it'll be f of y over f of x. But I'm solving for the angle, so it's theta equals the tan inverse of f of y over f of x. And if I plug those in, it's the tan inverse of f of y, which is 22.05 newtons, divided by 15.6 newtons. And I plug that in my calculator, I got 54.7 degrees. So my resultant vector of all these three, my net vector, is 27 newtons, 54.7 degrees. The way that I do it is I'm going to say that that's north of west, but the way that the problem's set up, it's always measured from 0. So if I were to think about that, that's 90 degrees, and that's 90 whatever minus that 54.7. So my other option is, or it's 27 newtons, 125.3 degrees. And that would be measured from 0 in this angular is a trig thing, but this is the positive direction. Counterclockwise is the positive direction. So this whole angle is 125.3 degrees. So either case, it's 27 newtons, either 54.7 degrees north to west, or it's 27 newtons, 125.3 degrees from the 0 point. So what we had to do is we took all the forces, we drew them out, but we broke them all into their x components and into their y components. Then we had to add all those components together to get a resultant x and a resultant y. Then we put those on its own triangle, and we solved for the hypotenuse, which is the magnitude of the vector, and then we had to solve for the angle to get the direction, and then or we can measure the direction from 0. So that's how you solve net force or net vector problems.